So Unit 5 is statistics. And there is a lot of material we could do on statistics. The hard part for me is going to be holding myself back. I will do my best with that. There is some preliminary stuff that I would like to go over, and I'll kind of skip through it really quickly, leaving out some of the details that are unimportant. If we were going into a longer statistics unit, we'd have to go through more of it. But anyway, for now, let's discuss what is statistics. Well, statistics is nothing more statistics is using a small group to describe a larger group. Now, in statistics, that larger group is what we call a population. That is the group of items that we wish to learn about, that we want to know something about. For example, if we wanted to do a survey or wanted to learn about WITC students, we would be looking at all students at WITC. Or if we wanted to learn about the next presidential election, that's usually a tough one. Presidential election, do we want to learn about everybody in the United States? What about the 12-year-old kid? Do we care about them for the presidential election? Not really. All registered voters? Well, even that isn't really quite what we would want for a population. If we're talking about the next presidential election, our population is actually all the people who will vote, that are going to vote in that election, which is tough to do because some of those people don't even know whether they're going to vote or not yet. This smaller group is what is called a sample. And that sample comes out of the population. Every member in the sample must be in the population. We can't take people from outside of our population. Otherwise, that sample is not a good one. We strive to make that sample what we call a representative sample. A representative sample means it has the same properties or same characteristics as that population. So if 1/3 of the people in the population prefer a certain candidate, then about 1/3 of the people in the sample should support that particular candidate to make it a representative sample. Well, next, what we're learning about these things, we said we're using the sample to learn about the population. What we're really studying is a population parameter. The parameter comes from the population, and it is a number that describes the population. If we say that 30% of all students at WITC have student loans, that's describing the whole population. Now, in the case of WIT students, it probably wouldn't be that hard to contact or dig up the information on every student at WITC. But if we go back to the presidential election, trying to figure out all the people that are going to vote in the next election, who they're going to vote for, would take too long. First of all, there's a lot of reasons why we do a sample instead of doing the whole population. One of them is just that time, and of course money is the other big one. So that sample, what we're gathering from that sample is the actual statistics. A statistic is a number usually that describes the sample. So if we take a sample and 40% of the people in that sample support a given candidate, that's a statistic that describes the sample. Now, a lot of times those statistics are used to estimate. Well, that's the whole purpose of doing the statistics, is to estimate that population parameter. So, statistics, types of statistics we're going to deal with. What we've been discussing so far goes under the category of pretty much descriptive statistics. Descriptive statistics are just that. You gather the information, use those statistics to describe the population. There's another type of statistics that's a little bit more useful, a little bit more powerful, called inferential statistics. Inferential statistics is where you take this information and use it to make some sort of a decision or try to predict the future in some way, predict how things are going to come out. So we have these different things we're going to do. We have the population, we have the sample. We need to talk about how do we get that sample, sampling. As we said, we want a representative sample. In other words, that sample has about the same characteristics as that population. To do that, we have to be careful about how we get the sample. The first thing is the size of the sample. It must be small enough that it's practical, but yet large enough that it's worth doing. If you have smaller populations, a lot of people say it has to be at least 5% of the population. But if you have a large population, again, like voters for the next election, that 5% would be way too large. So getting a proper size. The bigger the size, larger the samples means it's closer, those sample statistics are closer to the population parameters. Obviously, if you examine the whole population, well, then your sample statistic is exactly the population parameter. The second thing, other than size, is how are they chosen? Let's say you decide that their sample size is going to be 500, and you're going to go stand on the street corner and just ask the next 500 people to walk by who they're going to vote for. Well, that is not a good sample because you just took people that happened to be walking by at that point in time. First of all, it's only one location. You're not spread out amongst the region that's going to be voting on that, and you're restricted to a time frame. What about people that work at that time or people that have other commitments? You have to be able to spread it out so that you're getting what's called a random sample. What a random sample means is every member of the population has an equal chance. Of being in the sample. For example, you might write down the names of everybody in the population, throw them in a hat, and draw out however many you're going to put in the sample. That would be random. There are other random mechanisms, but that's one of those topics that we're not going to get into because of our time constraints here. So let's move on to now, once we have the sample and we start gathering data, what are we going to do with it? So I'm just going to put out a list of numbers here, and we're going to look at organizing those numbers. There's two types of data we're going to look at. There's numerical, sometimes called the fancy word for it is quantitative. And then there is categorical. And its fancy word is qualitative. Numerical, what we're looking at is a random variable. When we're doing any sort of statistical study, we're asking a question. And the answer to that question is a random variable. For example, if we're looking at heights of students, The question is, how tall is the student? And the answer is, 6 foot 2 inches or whatever. That answer is a random variable. Since that answer is a number, that would be a numerical variable. If we're asking, what's your favorite color? Well, the answer to that question would be red, blue, green, whatever. Since that answer puts you in a category, it's not numerical, that would be categorical random variable. So we're going to have to look at analyzing both ways, numbers and categories. Let's start out with numbers. So let's just take a look at, let's say the statistics test coming up. I'm going to group together my students from the last time I taught the course, and we're going to look at their scores. So let's say that the scores, and I'm going to put them in order from smallest to largest just because it's going to make things easier on us later on. What do we have there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I'll put one more down here. 14 people. So we have a list here of scores. Now I counted there are 14 of them. The first thing we're going to do is summarize these. The sample size, we use the variable n equals 14. Now we're going to come back in a little bit and talk about how to work with these numerically. For right now, I want to talk about how to organize them. This list has been put in order from smallest to largest, which makes it a little bit easier to look at. But if those numbers were just written down in the order we found them and they were not in order, looking at them, it'd be really hard to pick out, which one's the most common and, how the scores are distributed and stuff like that. So it's necessary to organize them a little bit. The first thing we're going to do is we're going to organize them into a table. This table is usually what's called a frequency table. And with numbers, there are two types of numbers we deal with. There are numbers that put you almost into categories, but they're still numerical, like how many cars do you own, or how many classes are you taking, where the answers are 1, 2, 3. And usually those, they're small enough because most people don't own more than a couple of cars. The range is small enough that you can list out each individual value, like 0 cars, 1 car, 2 car, 3 cars. And you can put that in the table. But then there's numbers like scores or heights and stuff like that, where there's just too many possible results. You can't list out each of them individually. The table would have a lot of numbers with a 1 for a frequency. So what we do is we group them. Those groups, we have to be really careful to have one of two things. Either they must be the exact same size, or they must have some relevance to the data. For example, we might group you by what your grade range is. So for your test scores, we might do it as, here's our range, or sometimes called our class. This is going to be our frequency over here. For test scores, we might list it as grade ranges. 77 to an 84 is a C. 85 to a 92 is a B, and 93 to 100 is an A. Now you notice this actually happened to come out that each of these has a range of 8 anyway. This goes from 77 to 84 is only 7, but you got to go 77 to 85 is 8. 85 to 93 is 8 as well. So all these ended up being the same size anyway when we did grade range. So here's a case where we met both of them. The categories, the ranges are all the same size, and they have relevance to the data. Now we need to count how many are in each range. Now one thing that I sometimes do if the numbers are not in order like these is I'll put a tally column in here. And what I'll do is I'll look at the numbers like, oh, we've got an 87, that goes here. A 94 goes here. A 91 there. And I'll put the little tally marks in, and it helps me count them up. Well, here we already have the numbers put in order, so we just have to go 87 or 77 to 84. There's 4 of them. 85 to 92. There's 3 of those. 93 to 100. 1, 2, 3, 4, 5, 6, 7 of those. So it's pretty easy to count them up when they're put in order. Hopefully the total here is 14, and it is. There's a total of 14. That is called the frequency. Now, there's sometimes something that's is just as useful or more useful called the relative frequency. And that's basically what you're doing is you're pretty much finding the percent or proportion of the total. For example, here, I would take the 4, which is the number of people that scored between 77 and 84, and I would divide it by 14, which is going to give us 0.2857143 approximately. That would be roughly 28.6%. I could either leave it as 0.286 or 28.6%. Either one is fine. 3 divided by 14, that would be the next one, which is going to give us 0.214287 approximately. Again, maybe rounded to 21.4%. Then 7 divided by 14, of course, is just 0.5. So that should be either leave it as a 0.5 as a proportion or 50%. Connection must be going bad. There we go. Sorry about the flickering there. So there's a frequency table. We have both, actually have both the frequency table. This part would be the frequency table here. And then adding this is the relative frequency table. That helps us decide, hey, there's 7 here. So the largest grade, the most common grade on that test was an A. But we can go further. We can take those tables and we can make it into graphs. For numerical data, there's a couple of different graphs. There's something called a histogram. A histogram is a fancy name for a bar graph. The difference is a histogram is a bar graph made of numbers. It's numerical data rather than categorical data. Most bar graphs we've done down on the bottom here, you'd list items like colors or whatever. Since this is a numerical set of data, what we're going to list down there are these number ranges, 7 to 84, or 77 to 84, 85 to 92, 93 to 100. Up the side, we're going to have a scale. The largest frequency here was 7, so we need to make sure our scale goes up to at least 7. So we go 1, 2, 3, 4, 5, 6, 7. So we had 4. If I draw my bars here, we had 4 that were in this group, 3 that were in this group, and 7 that were in that range. Now here we can very quickly look at this and see. Boy, the most common grade was the 93 to 100. The least common grade was the 85 to 92. We might do a circle graph or a pie chart. Now, a circle graph or a pie chart is more common when we're dealing with categorical data. So let's take a look at some categorical data, and we'll go through the frequency table, and then we'll go into the pie chart. So let's look at favorite colors. Let's say we surveyed a bunch of students to see what their favorite color was. And we're giving them a choice, red, green, or blue. So here we have a list of 20 responses, red, green, or blue. And here's a great example of how looking at the raw data can be deceiving. When you look at things, your mind can only focus on about 7 things at any given time. So when you're looking at a particular part of this, you're only seeing a certain portion of it. For example, if I look over at this part, I see a whole bunch of B's together, which would make my mind seem to think blue is the most popular color if I'm just looking at this. But if I'm looking in here, I see a bunch of R's, which would make me think red is the most popular color. Or if I'm looking down here, I see a pretty decent mixture, which would seem to tell me maybe they're all perfectly even. Well, let's see how close any of those approximations are. For our frequency table, it's going to be color and frequency. And I am going to put a tally column in here to make this one easier. We're going to red, blue, and green. So we've got a red, a blue, a blue, a green, a red, a red, a red, a blue, a green, a blue. Then we've got green, green, red, blue, red, green, blue, blue. Oops. So looking at this, that third statement we made where they're approximately equal seems to be it, because it's 7, 7, and 6 are the amounts that we have. So there is our frequency table. Now, if we were publishing this, we'd take the tally column out because that's just a working column. It's not really part of the final product. But for our purposes, we can leave it in there. Just like we did with the numerical, we could do a relative frequency, where we do the total here is going to be 20. So do each number divided by the total. 7 divided by 20 is 0.35 or 35%. 7 divided by 20 is still 35% or 0.35. 6 divided by 20 is 0.3. So there's our relative frequencies. We could do a bar graph of this as well. Bar graph could go either horizontal or vertical for categorical data. I tend to make things vertically because that's how numerical data has to go. And we have to go up to 7 again. So 1, 2, 3, 4, 5, 6, 7. Red was 7. Blue was 7. Green was 6. By the way, what I just did here is an example of really poor form because I made the graph correctly, but I did something that might have a psychological effect on the reader. What did I do? I made the bars green. And one of the choices down here is green. So by making the bars green, whoever's reading this graph tends to be drawn to the color green, thinking, oh, looking at this, well, this one's green, so green is, you're linking the color with the actual word, and it can be distracting. If we were doing a more thorough course, we would take quite a bit of time talking about misleading and deceptive or abuses of statistics. And that's one of them. When making graphs, there are a lot of little things like that that can be done to make graphs almost flat out deceiving. Still having true numbers and true data, but making them very deceiving to the reader. This is where a pie chart would be more appropriate. And in a pie chart, we go off of those percents. We had 35% blue, 35% red, and 30% green. In the old days, we would figure out, okay, we've got those percents. A whole circle is 360 degrees. You're going to find that percent at 360 degrees, and you're going to measure out that many degrees with a protractor and make it perfect. Well, right now, we have computer programs. If we wanted a perfect pie chart, we'd plug it into a computer program, and it would spit out the perfect chart. So for our purposes, all I'm concerned about is that we know some benchmarks. For example, half of a circle would be how much? 50%. A quarter circle? 25%. So we look for numbers that are close to each of these. Well, we had 35% for red. Well, 35% is closer to 50 than it is to 25. So we're going to draw it in like that. That is red. Well, blue was also 35%, so I'm just going to make it the same angle this way. This is blue. And actually, I got that a little bit off on it. It was a little big. Let me adjust those. There's the blue. There's the red. It says closer to 25 than it is to 50, so it should be a little closer to 25. And then what's left over there is the green, which is 30%. Now I screwed up a little bit. These are all numbers that are so close together, it's really hard to see a difference on the pie chart. But the pie chart is good as far as being able to identify really quickly which one has the bigger slice. And a pie chart usually does show percents. It's percents of the whole object or the whole amount. Like budget, what percent of your budget goes for heat, or what percent of your budget goes towards maintenance and stuff like that. The next type of graph we're going to look at doesn't really fit in with either of those types of data. It's called a line graph. A line graph doesn't look for different responses. What it looks for is how many people have a certain characteristic at a given period of time, and it follows it over a period of time. So for example, we might look at number of students taking this course. So we might have 2009, which is the first year of the course, 2010, 2011, 2012, and 2013. Can't do 2014 because it's not done yet. We're going to label up to 25. Let's say in 2009, we had 12 people take the course. 2010, it went up to 21. 2011, it dropped to 9. In 2012, it was up to 19. 2013, it was up to 25. We connect those dots together with a line. Now this line allows us to do two things. First of all, we can very quickly identify where the numbers were increasing. On those 3 time frames, the numbers were increasing because the line slopes upward. And then where it was decreasing. In that time frame, it was decreasing. The line slopes downward. The other thing it can do is it can allow us to relatively quickly identify where it's increasing the fastest. Here, the line is the steepest, so that appears to be the point where it is increasing the fastest. Now, for one of the weaknesses of graphs, we talk about graphs. The strength, of course, of graphs is you get very quick comparisons. You can very quickly find out which one is the largest or which one is the smallest. Or you can compare two. Out of these two, which one is the larger or smaller? You can compare them very quickly with a graph. The weakness of a graph is you can't find exact numbers. Even in this graph here, it's really hard to tell. Was that 21 or 22? As you get into larger numbers, where maybe this goes up by hundreds instead of fives, now it's pretty much impossible. Is that 121 or 123, or what is it? So the graph is just quick estimates for quick comparisons. It won't give it. If you need exact numbers, you have to go back to a table or the raw data. Well, enough of organizing this data into the graphs and stuff. Let's start looking at numerical summaries of data. So if we have data, there's 2 things that we're going to use to describe that data numerically. First of all, let's talk a little bit about data distributions or number distributions. A number distribution just is a list of all the possible values. So from the smallest, called the minimum, to the largest, called the maximum. And it's just a curve, and the height of the curve is the number with that value. So the higher the curve is, the more items in the population or sample had that value. So for most curves, it's really low out here where the minimum is, and it's relatively lower than the maximum. So there's very few items that are at the smallest and largest values. Most of them tend to be in the middle. So we can see here, this is the highest point of the curve right here. So that is the value that had the most number of things that had that particular characteristic, or that particular value. Most data distributions are shaped like a bell. I'm sure you've heard of the bell curve. The statistics is actually called the normal curve, or normal distribution, because that's how things in nature are normally distributed. Most of the values are towards the center, and as you get further away from the center, there's fewer and fewer items that have that value. So when we describe this curve, there's two things we need to describe. One is the center, because we're going to have a curve like this and a curve like that. They're identical curves, only the center of this purple one is moved over a little bit. It's in a different spot. The second thing is spread, or dispersion, it's sometimes called. This green curve has the same center as our original black curve. It's just narrower. It has less spread. So let's look at a set of numbers and let's calculate center and spread. We'll start with center. I'm just going to do a pretty easy list of numbers. So we'll start out with this. First of all, for this list of numbers, n equals what? Anybody remember? 1, 2, 3, 4, 5 numbers. N is the number of numbers in the list. So n equals 5. So for measures of center, the first measure of center we're going to talk about is the mean. The mean is what most of us think of as the average. You will add them up and divide by how many are there. So divide by 5 in this case. So it's 30, 44, 59, 62, 82 divided by 5 is going to be 16.4. That's our mean. Any questions on the mean? Let's do the median. The median is the middle. So to do the median, we have to put them in order from smallest to largest. So we'd have to put them 12, 14, 15, 18, 23. So that's step one. You put them in order. Second, you find the middle. I can cross off the smallest and largest if I want to. What's left in the middle? 15. 15 is my median. The other way we could have found the median is this. N equals 5. You take n times 1/2. So 1/2 times 5 is 2.5. That's telling us you round up to 3. The third number in the list is the median. Now the mean and the median turn out to be different here. The mean was 16.4, the median is 15. In a well-distributed set of data, those two numbers will be the same. Now there's a third estimate of center that we're going to talk about called the mode. The mode is the number that occurs most often. As is the case with most small sets of data, this set of numbers has no mode. There is no number that occurs more than once, so there's no mode in this set of data. The mode is usually a pretty weak predictor of center anyway. There's another one we'll call the mid-range. The mid-range is simply taking the smallest number and the largest number and average them together. So the smallest number was 12. The largest was 23. Add them together, you get 35. Divided by 2 is 17.5. That'd be the mid-range. And as you can see, that again is a little bit different than our other two measures we had calculated. The mid-range is, again, another quick estimate, but not really good. So as far as the best measure of center, it comes down between the mean and the median. Well, there's a lot of arguments between them, which one is the best. But let's do this as an example. I'm going to add a number to this data set. So we've got the 12, 14, 15, 18, and 23. I'm going to add the number 35 to this data set. So now if I add these up to find the mean, I add those up, I'm going to be dividing by 6 this time. Adding those up would be, what, 87, 117 divided by 6, which would give me 119.5 approximately. The median, remember median is location. They're in order now. N is now 6. So we take 1/2 times 6 is 3. Up here, when that came out to be a decimal, we rounded up to the next number. If it comes out to be a whole number, that tells us the median is actually between that one and the next one, the fourth one. Here's the third, here's the fourth. The median is between 15 and 18. We're going to average them together. It's 16.5. If we look at what happened here, what we did is we added in a large number. The 35 was way bigger than the rest of the numbers in the list. If we look at what happened, the mean went from 16.4 all the way up to 19.5. It changed by over 3. Where the median went from 15 to 16.5. It only changed by 1.5. The median is what we call a more stable predictor. It doesn't change when we put in extreme values, numbers that are way larger or way smaller than the rest. It doesn't change as much. Let me show you an example of this. 1984. University of Virginia. Published that the average starting salary for a graduate from their 4-year marketing program was right around $78,000 a year. Now that's pretty good money for starting salary. That's really good money for starting salary right now. Back in 1984, to put it in perspective, your average high school teacher was starting out at around $17,000 a year right out of college. That's really good money for just a 4-year marketing degree. Well, what they neglected to tell you there, this was actually the mean. And in that group of students, there was a man by the name of Ralph Sampson. And I'm guessing that most of you are either too young to remember Ralph Sampson or not sports fans. Ralph Sampson was 7'2", was the 2-time NCAA basketball player of the year, was drafted #1 by the Houston Rockets, and given a multi-million-dollar contract. But he still graduated from the 4-year marketing program that year. His salary got averaged in the mean with everybody else's. The median was $26,000. Mr. Sampson was the only person in that group that made more than $33,000 that year. So there's an example that shows why the median is a more stable predictor than the mean. Now it's a little bit early, but that's a great place to take our break, so let's do it.